So hello, welcome back students. So today we'll be starting the last chapter of your physics course BS PH 201, that is Statistical Mechanics. Okay, Statistical Mechanics. Okay, statistical mechanics. So what is the statistical mechanics? Why do we have to study this? Okay, so statistical mechanics, I mean, in very short, if you write, that is quantum mechanics. Okay, quantum mechanics plus statistics. Quantum mechanics plus statistics is equal to statistical mechanics. Quantum mechanics plus statistics is equal to statistical mechanics. Okay, now what is that actually? Why are we studying this? Okay, so basically it is the branch of science. It is the branch of science which establishes, this is a branch of science which establishes the interpretation, of the macroscopic behavior of the system. Macroscopic behavior, which establishes the macroscopic behavior of the system in terms of its microscopic behavior. Okay, in terms of its microscopic behavior, which establishes the macroscopic behavior of the system in terms of its macroscopic behavior. Okay, now I should tell something more before this actually. Now, what is this macroscopic behavior of the system? So let us give the very simple example, like in your class, that is EC3, which I take. Okay, in this class there are how many students? I think there are around 65 students are there. Okay, now there are 65 students, all are different from each other. Okay, all behave in a different way, but in a broad sense, you all are what? You all are EC people. You all are EC third batch of first year. Okay, so like for example, you all are doing during the sports. You all are doing. There is I mean, there is first year, there is second year, there is third year. Okay, all are doing March past. Okay, so I mean, say suppose first year is doing March past. Okay, so there are say 30 students in the group. Now each student are different from each other, but in a whole thing, all of you are same. Okay, because you represent first year. So this is also that kind of thing, the macroscopic the behavior. You all are the EC3 as a whole is a macroscopic quantity, and microscopic quantity is what? The students in it. Okay, so suppose for example, say in a in your classroom, I mean, we are dealing with atoms. Okay, so I mean, say there are Avogadro number of atoms, 6.023 into 10 to the 23 number of Avogadro, that is 6.023 into 10 to the 23 number of atoms are there in the classroom. Okay, so now we want to describe the motion of all these gas atoms, and we want to find the solution. So that is very, 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 I'll not say very difficult, but I mean very time taking, and it is very, very complex actually. It will take a lot of time to solve all the solutions. Okay, so so there okay, so therefore it is impossible to solve the problem of a macroscopic body. Okay, macroscopic body. Macroscopic, as I said in quantum mechanics also, that is a large body. Okay, a large body, a macroscopic body. A macroscopic body consists of microscopic bodies. Okay, that is a large body consists of microscopic bodies, that is electrons, protons, neutrons. So it is not possible to find out the like the simple thing actually. I mean if you want to a human body is consisting of millions and millions of microscopic particles, that is electrons and this. So is it possible to calculate to do the differential equation of each electron and then solve it? It's not possible. The easiest way is what? You take the macroscopic body as a whole, that is the person as a whole. Okay, you take the person as a whole, and then you calculate all these parameters by solving the motion of the person as a whole. Okay, how is the person, how is the man walking or running? Okay, instead of calculating the differential equation of the electrons by which the man is made up of, you calculate the motion of the man as a whole. So that is the thing. So therefore it is impossible to solve the problem of a macroscopic body consisting of 6.023 into 10 raised to 23 atoms with their electrons. Okay, such problems can be successfully solved. Such problems can be successfully solved by the methods of statistical mechanics. Okay, by the method of statistical mechanics. Those kind of problems can be successfully solved by the methods of statistical mechanics. Okay. Now so how can this be solved? Okay, so it is not concerned I am writing this you just to make you all understand. It is not concerned with the motion of the actual motion of particles constituting the system. Okay, it is not concerned with the actual motion of the particles constituting the system. Rather, rather it investigates. Rather, it investigates uh, some average or most probable, some average or most probable properties. Rather, it investigates some average or most probable properties of the system. Most probable properties of the system. Okay, without most probable property of the system without going through detailed detailed description of the constituent going through detailed description of the constituent particles Okay, so here only it is written that it is not actually concerned with the actual motion of the particles constituting the system. Okay, it is not at all concerned with the particles by which the system is constituted. That is, man is constructed by the electrons and protons in here. It is not concerned with that. Rather, it investigates some average or most probable properties of the system. Now, you are not. I have given just the example of the man, but here you are not actually concerned with the man, but you are concerned with a system of gases. Okay, an enclosure consisting of a gas. Okay, so it investigates some average or most probable properties of the system. Now, what is this average or most probable properties of the system? You will understand as I proceed forward in the chapter. Okay, rather it investigates some average or most probable properties of the system without going through detailed description of the constituent particles. Just it identifies the most probable properties of the system, most probable behavior, or the average behavior. Okay, just average you can try, like for the I mean your class, the average of the students, average of the 65 students of EC3, how they behave. We are concerned with only that only, nothing else. We are not concerned with the behavior of each student individually. We are concerned with the average behavior kind of thing. So I think I'm little bit being able to give you the how this statistical mechanics works. Okay. Uh, so how will this work then? So the larger the number of particles, definitely the more the number of particles. So since you are doing the average, so the more the number of particles, the more accurate the result will be, right? So similarly for statistical mechanics also, the larger the number of particles, the larger the number of particles in the system, larger the number of particles in the physical system, the larger the number of particles in the physical system, okay, considered in the physical system considered, the larger the number of particles in the physical system considered, the more nearly correct are the more nearly correct are the statistical the more nearly correct are the statistical prediction. The more nearly correct will be the statistical prediction. So it's very obvious. The more that is why we are doing statistical mechanics here with a large number of particles. The more the number of particles, larger the number of particles in the physical system considered, the more nearly correct are the statistical prediction. Okay. So uh, these are the things. Now what happened here also, like this has got classical statistics and quantum statistics. Okay, statistical mechanics has also like in quantum mechanics also, at the very beginning when we are doing, that is means you had got Wien's distribution law, right? Then Rayleigh-Jean's law, all were done through basically what, classical consideration. Okay, so here also, I mean, uh, before the advent of quantum theory, so before the advent of quantum mechanics, just like while quantum mechanics which I was doing, that is when in the classical world, when there was Newtonian mechanics, classical mechanics, these scientists or the other scientists who had the experience, Maxwell, Boltzmann, Gibbs, etc., applied statistical methods. They are also they needed this to find out the statistics. So applied the statistical methods, uh, making the use of classical physics. Okay, these statistical methods are known as classical statistics or Maxwell-Boltzmann statistics. You will study about that later. I am just giving a small introduction here. I have written a lot of things. Okay, they did all these statistical problems by employing Maxwell-Boltzmann statistics. Okay, so these are called as classical statistics. But again, just like quantum mechanics, classical statistics explain classically observed phenomena like temperature, pressure, energy, etc., but could not explain other phenomena like black body radiation. Then black body radiation, it could not explain. Black body radiation is basically photons. Okay, uh, the mechanics of photons, this could not explain. Then they could not explain Compton effect, specific heat at low temperature, they could not explain. For explaining such phenomena, Bose-Einstein and Fermi-Dirac statistics were developed. Okay, for explaining those things, Bose-Einstein and Fermi-Dirac, Bose-Einstein and Fermi-Dirac statistics were developed. Bose-Einstein and Fermi-Dirac statistics were developed. Okay. So these I will, the Fermi-Dirac, Bose-Einstein, Maxwell-Boltzmann, these all I will describe little bit later. Okay. So now I'll start the chapter. So for this you need some little bit understanding about energy level. What are energy level? Okay, energy level and energy states. Energy level and energy states. Okay, energy level and energy states. So to understand what are energy level and energy state, let us consider a hydrogen atom. That is the easiest atom. Hydrogen atom consists of what? Hydrogen atom consists only one electron in its extranuclear orbit. Okay, and its energy is given as En is equal to minus 13.6 by n square. Okay, okay. Now, so how will you do that? So let us do like this. Let's draw a table. Okay. Okay. 1, 2, 3, 4, 5, and 6. Okay. So here is the n value. Okay. Here is the n value. What is n? N is basically the energy level. Okay. N is basically the energy level. What is the energy? That is the orbit. Okay. So you know all these things. I am just recapitulating all these things which you had studied in class 11 and 12. Okay, n value is the just I mean, suppose this is the nucleus, so this is the first orbit, n is equal to 1. This is the second orbit, n is equal to 2, like that. Okay, acha. So for a particular n value, there will be L. Okay, L value. What is L? L is the orbital quantum number. Okay, L is the orbital quantum number. I think most of you know this orbital quantum number. For L value, there will be ml. Ml is the magnetic orbital quantum number. There will be ms value, spin orbital quantum number. Then there will be the corresponding energy states, and here there will be the number of energy states. Okay, so say for n is equal to 2, n is equal to 2 level. Okay, so n is equal to 2, what will happen? L will be what? L will be 0 to n minus 1. Okay, L will be here, L will be 0, 1, 2, 3, 2, n minus 1. Okay, ml will be what? Ml will be minus L, 2 plus L. Okay, ms will be very easy, minus half plus half, always. Okay, acha. So now L will be what? L will be for n is equal to 2, L will be 0 and 1. Okay, so let's see what happens for 0. For 0, again ml will be what? Ml will be minus L to plus L. So 0 only. So ms will be plus half and and minus half. Okay, so energy states will be what here? Energy states will be 2, 0, 0, half, and 2, 0, 0, minus half. Okay, so here number of states will be 2. Okay, so similarly for this 2 thing, another will be what? 0 to 2 minus 1, that is 0 and 1 will be there. Okay, 0 and 1. Okay, acha, so ml will be what? Ml will be, so minus L to plus L, so minus 1 to plus 1. So first will be minus 1. Okay, minus 1, and this will be plus half minus half. So this will be what? This will be 2 states will be 2, 1, minus 1, plus half, and 2, 1, minus 1, and minus half. Okay, so it will be 2. Again there will be 0 minus 1 minus L2 plus L, so minus 1 0 and plus 1. So for this one it will be what, ms will be plus half minus half. Okay, so this will be what, 2 1 0 half 2 1 0 minus half. So there will be two states like this. Acha, and this one, here there will be what, plus 1. Okay. So this will be what, plus half minus half. So this will be what, 2 1 1 plus half and 2 1 1 minus half. Okay, again the states will be again here 2. So total for L is equal to 0, total number of states is 2. For L is equal to 1, total number of states is 6. Okay. So now this n is equal to 2 is called what? N is equal to 2 is the these are the principal quantum number. This is the principal quantum number. Okay, so you see here, if you put minus 13.6 by n square, so this will come a constant value. Okay, so what are you seeing here? For n is equal to 2, this quantum number, that is this energy level. Okay, there are how many states here? There are in total 8 different states. 1 2 means 2 plus 2 plus 2 plus 2. There are 8 distinct states having the same energy, Okay, so what are these called? Such type of distinct energy states having the same total energy are called as, what I did in the particle in a 3-dimensional box, degenerate states. Okay, let me write it for your benefit. So for n is equal to 2, we get 8 distinct, for n is equal to, we get 8 distinct energy states. For n is equal to 2, we get 8 distinct energy states. But all these energy states have the same value. All these energy states have the same value of the total energy. All these energy states have the same value of the total energy. Okay. Okay, I showed you only because 13.6 minus 13.6 by n square, it depends only on n, it does not depend on ml and l and all these things. Okay, so it depends on only n. So here it has the total energy, so have the same value of the total energy. Okay, so such type of distinct energy states, having the same value of total energy, such type of distinct energy having the same value of total energy are known as degenerate states. Okay, and see here, all these 8 states, these are the energy states. All the 8 states will have the same value. I think the those who did not little bit understand your degeneracy in the last chapter which I taught, quantum mechanics, three-dimensional potential well. You can understand this a little bit more. Okay, so are known as degenerate states. Okay, and it is said, okay, and it is said that that n is equal to 2 level is 8-fold degenerate. Okay, n is equal to 2 level is 8-fold degenerate. Similarly, we can tell that n is equal to 3 is equal to 18-fold degenerate. N is equal to 3 is equal to 18-fold degenerate. Okay. Achha. Now, I mean, quantum mechanics has already started. Sorry, statistical mechanics has already started. Okay. Now, basically, we'll do till now we'll do classical statistics only. Later on, we'll shift to quantum statistics. Okay. So, achha. So, what are the things? Macrostates and microstates. I have to tell a lot of things to these are not very difficult to understand, but I have to give many examples to make you understand. Macrostates and microstates. So here, as I told you, that this thing, that is rather it investigates some average or most probable probabilities of the system. Okay, what are these actually most probable probabilities? I said I'll tell it to you later. So now you will study all these most probable probabilities. Okay. Acha. So now let us start it. Acha. Now I mean these are statistics is basically what I mean I mean doing various permutations and combinations and counting the average behavior. Okay. Okay, so let us consider two boxes like this. Okay, let us consider here like this two boxes. Okay, like this, and let us consider here two balls. Okay, let us consider two boxes and let us consider two balls which are indistinguishable. Indistinguishable. These are very important things. Indistinguishable. Okay. How will you find indistinguishable? Like suppose they are red and green, but in your eye, some तुम्हारे आँख में पट्टी बंधा गया है. Okay, so the balls will appear to you that they are indistinguishable, or you can tell that there are two I mean steel balls only of the same color, or they are indistinguishable. Okay, so how will you arrange them? Right? How will you arrange the balls in these two boxes? So how will you arrange them? So in here you can put two balls here, and in this box will be empty. Okay. Achha. Then in this box you can put one ball in one box, another ball in another box. Okay. Achha. There will be another combination. In one box here you will put 0 balls, here you will put 2 balls. Right? So these are the various permutations in which you can keep. Right? These are, remember, the balls are indistinguishable. Let us take two balls which are indistinguishable, balls. Okay, so how can you do that? Either you take two balls of the same size, same color, okay, two ivory balls or two steel balls, or you can just tie a rope or tie a piece of cloth in your eyes so that you cannot see its color. Okay, so balls are indistinguishable, and there are two boxes. So in the left box you can put two balls, in the right box 0. In the left box 1, right box 1, left box 0, right box 2. Okay, so what you can write here? So here the number of arrangements, is equal to what? 3. Number of arrangements is 3. So how you can write that? You can write it as 2 plus 1. Number of arrangements you can write as 2 plus 1. Okay, so now suppose they are distinguishable. Suppose they are distinguishable. Suppose these balls are distinguishable. Distinguishable means suppose there are, red and green balls. Okay, now they are of color, means you remove your cloth from your eye, or you take the color, the balls are only of different color. Okay, so how do you adjust them? Okay, they are now distinguishable. So here you will put red and green, here nothing. Okay, here you see nicely that here you can put red here and green here. Here you can put green here, red here. Okay, you can put this. You can write this below also. I have just written it here, so there is not a big issue here. Okay, here you can put 0 balls. Here you can put all the 2 balls here, red and green. Right. So here, how you can write number of arrangements? Number of arrangements will be what? 1, 2, 3, 4. 4. So how will you write? 2 square. Okay, number of arrangements is 2 square. Acha. Now you see here that there are how many how many states here? How many for the indistinguishable thing? How many states are there? 1, 2, 3. Okay, so what will be the probability of this state? This state will be 1 by 3 probability. Okay, 1 by 3 probability. This will be 1 by 3 probability. This will also be 1 by 3 probability. Right? That's it. Now this one, here there are how many states? 1, 2, 3, 4. So this will be 1 by 4 probability. This will be 1 by 4 probability. But this one will be how much? This is 1 by 4 plus 1 by 4. That is, this state. This is a state. So these are states. So one is in one box, another one is in another box. Here you have got 2 states like this. So this probability will be what? 1 by 2. Right? The probability will be 1 by 2. So this state is called as the most probable state. This state is called as the most probable state. Okay. Let us take now another example. Let us take 3 particles. Okay. Let us take now 3 particles. So how will you do? Let us take now 3 particles. This will be, first one will be indistinguishable, and this one will be distinguishable. Okay. So how will you do that? So here there will be 2 boxes. Okay, here there will be 2 boxes. So the three particles are in the left one. Here there is none. Okay, then 2 particles are in the left one. In the right there is none. There is 1. Okay, then in the another one particle is in the left box. There are 2 particles here. Then another one is there are 0 particles in electron, here are 3 particles. Okay, so how you can write this? There are total how many states? 1, 2, number of arrangements. Again here number of arrangements. Number of arrangements is equal to 1, 2, 3, 4. So how you can write this? 3 plus 1. You see, number of particles plus 1. Okay. Again, the probability. What is the probability? You see here, this is 1 by 4, this is 1 by 4, this is 1 by 4, this is 1 by 4. So equal, all equal probability. Acha. Then here, this box if you do, all the 3 are in one box. R, G, there are 3 balls distinguishable. So here you have taken red and green. Here let us take another one, blue. So red, green, blue, and here there is 0. Okay. Achha. Then you take say red and green are here and say blue is here. Okay, and another one is say red and blue are here and green is here, and another one is say green and blue are here and red is here. Okay, so these are the three three states. Okay. Achha. Another one is say here red here, green, blue here, green here, red, blue here, then blue here, red and green here. Okay, so these are the states. Okay, and another one will be, the last one will be what? Last one will be 0 is here and red, green, blue are here. Okay, so what will be the state here? So this how many total states? Achha, you've seen number of arrangements. Number of arrangements will be what? Number of arrangements will be just 6 plus 2, 8. How you can write 8? 2 cube. Okay. See, 3 is the number of the material, number of the particles. Okay. Achha, here the probability of this one will be what? Probability of this state occurring. This is the probability of this state. So this state occurring. How many states are there? Total 8. So 1 by 8. Okay, 1 by 8. This one will be what? This state will be what? 3 by 8. This one will be 3 by 8. Okay. Means 2 in this box, 1 in this box. This is 3 by 8. 1 in this box and 2 in this box. This is 3 by 8. And this one will also be 1 by 8. Okay. Achha. Here again, these two states are the most probable states. Okay, this one will be the most probable states. Okay. Achha. So so in this way this thing goes on. Okay, in this way this thing goes on. That is, these are the most probable states. Achha. So now you see that as the number of particles are increasing, the probability is gradually decreasing. Here the probability was what? 1 by 4. That is, 1 by 4 is 25%. Here in the this is 1 by 8. 1 by 8 is how much? Less than 20%. Okay, 1 by 8 is less than 20%. 8 ones are 8, 10 ones is 2, 8 to the 16. 12 to 13% it is. Okay. So as the number of particles are increasing, the probability is gradually decreasing, and these are the most probable states. These are the most probable states, means the states which are occurring more. Okay. Acha. uh, Acha. Now, what are the macro states? What are the macro states? Macro states are, what are the macro states? The most important thing I have to tell now. These are called as the macro states, indistinguishable part. See here, indistinguishable. These are called as the macro state. Corresponding to a particular macro state, there are a number of microstates. That is, here there are 2 particles in the left box, and right particle there are 0. So when you do distinguishable thing, then you take this one, this RG0, and in the left hand side, one particle in the left box there is 1 particle, right box there is 1 particle. So in this thing there are 2 types of arrangements. That is, in the left there is right there is green, in left there is green, right there is red. There are 2 arrangements. So corresponding to a particular macro state, there will be a number of microstates. There can be the same number of macro state. The number of microstate can be same as that of the macro state, but not less than that, and it can always be greater than the number of macrostates. Okay. Achha, so these are the macrostate and microstate. So I mean, if you write it simply, very simply, macrostate is the arrangement. Macrostate is the arrangement of the particles. Macrostate is the arrangement of the particles of a system. Macrostate is the arrangement of the particles of a system without distinguishing. Macrostate is the arrangement of the particles of a system without distinguishing them. Okay. Macrostate is the arrangement of the particles of a system without distinguishing them. Okay, without distinguishing them. And microstate is the arrangement of the particle with distinguishing them. Okay, microstate I am writing in short. Microstate is the arrangement of the particles, of a system with distinguishing them. Okay, with distinguishing them. As now for n particles. Now let us do for n particles. For n particles, what will you do? For n balls. For n balls, how will the arrangement be indistinguishable? Indistinguishable, here there will be n0, then here there will be n minus 1, 1, here there will be n minus 2, 2, okay. So like this, here there will be n minus r, r, okay. Then here there will be 0 and n ultimately, okay. So the probability of each of the states will be what? 1 by here the probability is what? 1 by 3. So 1 by 2 plus 1. So here there will be 1 by n plus 1. This one also 1 by n plus 1. This one also 1 by n plus 1, like this. Okay. And the number of microstates. The number of microstates will be what? The number of microstates the number of microstates will be n factorial by r factorial into n minus r factorial. Okay, number of microstates will be n factorial by r factorial into n minus r factorial, and probability of the microstates will be what? Probability of the microstates. Probability of the microstates, that is, these microstates will also have a probability like this: 1 by 8, 3 by 8. Now 8 is what? 2 cube, that is 2 to the power n. See, 2 to the power n. So this is number of microstate, and this will be what? N factorial by r factorial n minus r factorial 1 by 2 to the power n. Okay. Achha. So I mean, these are the thing. Now I mean, the simple thing is that number of macrostates will be what? It will be n plus 1, that is, n is the number of particles plus 1. Achha. And number of microstates will be what? Number of microstates will be, for any bed, it will be 2 to the power of n. Okay, number of microstates will be 2 to the power of n. This will be for, means, this will be for general formula. This is the general formula. Okay, this is the general formula for number of macrostates and number of microstates. This is the general formula for number of macrostates and I mean, this will be for n particles. Okay, so these are the things. Okay,